Hello everyone, in this video we are going to talk about 2D elements. So we reduce our three-dimensional models to 2D models based on the assumption of plane stress, plane strain, and axisymmetric. Our elements can be either triangular or quadrilateral, and we can have first order that we refer to as linear, second order or quadratic, and higher order. As we increase the order, the accuracy increases as we have more nodes and more degree of freedom. But it comes at a cost of higher computational cost. So there's always a trade-off whether we are using lower order elements or higher order elements. For triangular elements, a linear element has 3 nodes and a quadratic element has 6 nodes. For quadrilateral elements, we are dealing with 4 node and 8 node elements. We use 2D models in general when our nodal variable depends on both x and y direction. In 1D, let's assume we had a 1D model, a cantilever beam, that if the displacement only depends in one direction, we can use 1D. But if the displacement depends both in x and y direction, then we have to use a 2D model. In this example, I'm showing you a quadrilateral element with the nodal variables of temperature. So here the temperature is function of x and y. The temperature changes as we move in x direction as well as y direction. We can define local coordinate x, y, and also global coordinates. So for local or natural coordinate, we use the Greek letters C, eta. Here it's 2D, so we don't need theta. And in global coordinate, we use x and y. The origin of our local coordinate is in the center, and the global coordinates begins from one edge. And these are the conventions that we use, and we develop our shape functions based on these conventions. But there is no specific reason that we choose these coordinates and at these locations. So here on this edge, Kc would be -1, and eta -1. When you move to j, Kc would be 1, eta would be -1, and then same for the rest of our nodes. Our first task is to find the shape function, or we call them interpolation functions, because interpolation functions interpolate between our nodal variables. If we have the nodal variables here, let's say we have uj, ui, un, and um. If we want to find the displacement in any direction, in any random location within element, we have to interpolate. And to interpolate, we need interpolation functions. The simplest one is if we use a linear interpolation. Because it's 2D, we need to have both x and y coordinates. And if you want to write it in terms of local, instead of x and y, we use Kc and eta. But in linear interpolation, we have 4 unknowns from C0 to C3. But also we have 4 boundary conditions at each node. So if we apply the boundary conditions, we can find our unknowns, our coefficient. And node I, or at Kc -1 and eta -1, our nodal variable is ui. At node j, we have another boundary condition, the displacement of node j, and node m and node n gives us the other 2 boundary conditions. So plugging in the boundary condition will give us the unknown coefficient, C0 and C3, based on our nodal variables. So we can write our displacement function as function of shape functions and nodal variables. So as you can see, u is function of Kc and eta. That means that at any location, if we plug in the value, the coordinates of our point of interest, we can find the displacement for that location. Our shape functions are based on Kc and eta, and these are the values that we have. They are constant values at nodes. So here I'm listing you the shape functions, or the coefficient of our nodal variables based on the global coordinates. So we have x and y, and based on the local coordinate, we have Kc and eta. And here is the geometry that you can see the relation between the two coordinates. Because in linear quadratic element, we have 4 nodes, therefore we have 4 shape functions in each case. If you want to plot the shape functions, because we are dealing with 2D, therefore we have surfaces. But the properties of shape functions are the same. There are 1 at their nodes and 0 at any other nodes. And at any location, the addition of the shape functions would give us the value of 1. So here we have node n, m, I, and j. And then we have a corresponding shape function for each one. I've just plotted those equations in xy coordinate. So here we're going to look at an example. Nodal stresses are given for the linear quadratic element. Find the stress in the middle of element. So we have the stresses at each node here. So here is a function stress as a function of our coordinate, xy coordinate, and we want to find the stress in the middle. And that's the definition of interpolation function. That's the application of interpolation function. If we have the values at the nodes, we can find a value at any other location. So if we write our equation, stresses are function of our coordinate, so we can plug in any coordinate that we want. Here we want the middle of the element, so we know our shape functions are developed based on the assumption that our local coordinate of Kc and eta have the origin in the middle. So that means that Kc and eta are 0 for us as function of the shape function and nodal variables. We have the nodal variable. The problem has given us the nodal variable. So we just need to find the shape functions. And shape functions are based on the coordinate, so plugging the coordinate. I'm just showing you for ni, but it's the same for others as well. If I plug in 0, I get 1/4. So our stresses will be 1/4, 1/4, 1/4, 1/4 on my nodal stresses. So if I factor 1/4, it's just addition of these stresses divided by 4, or the average of the stresses. And I get the value of the stress in the middle. Because we want to find the stresses in the center of the element, and we are using a linear quadratic element, so the stress in the middle is simply the average of the stresses. But this equation gives us the value for any coordinate that we want. If we want a different location, we can find that. And that's the application and the reason that we use shape functions. We can use higher order elements. So instead of only 4 noded elements, we can use other elements in the middle of each side and have 8 nodes. Because we have 8 nodes, we are going to have 8 shape functions, and our shape functions have higher orders, as you can see here. So the question is that, is it better to use one quadrilateral element, or let's say we use 4 linear quadratic elements? If we use one quadrilateral element, at the end we are going to have a smaller stiffness matrix, because 4 linear quadratic element, we are going to have a node here as well, and each node is introducing degrees of freedom, and that degrees of freedom will appear in our stiffness matrix as well. So we are going to have a higher order of our stiffness matrix. That's the main difference. The other difference is that 2 linear elements are not necessarily equal to quadrilateral elements. Similar to 1D, let's say I have a 1D element, this one is quadratic, which means that it can describe such a shape. If I model it by two linear, so one linear here and then another linear here, of course these are going to be on top of each other, that would be two linear. So you can see two linear are not necessarily the same as a quadratic. The quadratic shape is different. So quadratic quadrilateral is different than four linear quadrilateral, but the results are very close. And it's up to you to judge what you're going to use. But generally, if you have a model with one element through the thickness, if you have a model that you can only model one element through the thickness, then it's better to have a higher order element here, because that's all we have. We have only one element. And so let's have that element as a quadratic element or cubic element if we can. So we can have some variation through the thickness as well. So our model could capture whether displacement variation or stress variation or whatever our desired output is. Here I'm showing you the shape of our shape functions. Because it's quadratic, so the surfaces are also quadratic, but the properties are the same. So we have our nodes I, J, I, K here, J, L, M, O, N. Here we don't have anything because we don't have any center nodes. And the value of shape function is 1 at its node and is 0 at any other nodes. And that's true for the other shape functions as well. We can go and model our element with higher order. We just need to include the correct coefficient and the correct component. For a 1D, it's very simple. We have a constant value that usually is C naught, and then we have C1x, C2xy, and C3xy. So we have 4 components. That's 1D element. If you want to go higher, then you need to make sure that you have a component for y squared, x squared, xy squared, x squared y, x squared y squared. So this is a Pascal triangle that tells us what components we need to include if you want to go to higher order. As we talk, we mainly stay with linear and quadratic. Even software such as ANSYS, Abacus, they do not have many elements for cubic interpolation. But if you want to, if you have an application that require to use higher order interpolation functions, you can come to the Pascal triangle and it tells you what components you need to have. So the number of nodes, we can use this equation, p plus 1 squared. That means that if our element is linear, p is 1, 1 plus 1, 2, 2 squared would be 4. So we have 4 nodes. If p is 2, 2 plus 1, 3 squared, that would be 9 nodes. So if you look at this image, you can see that we have interior nodes as well. So interior nodes are kind of special in a sense that they are not shared with other elements. If we have another element here, they do not share that interior nodes. So elements that include these interior nodes are called Lagrangian elements. So this Lagrange, that means that we have interior nodes as well. They are not very common. They are actually becoming extinct. I see less and less of these elements in the softwares and in the research area as well. So if our element does not have that interior nodes, they're called serendipity element. So the terminology is very important. So remember the difference between Lagrangian and serendipity elements. The difference is that interior node. For 1D, here I'm not showing you because for both cases, they're the same. When it comes to quadratic, then there is a difference between serendipity and Lagrangian. Serendipity has only 8 nodes, Lagrangian has 9 nodes because it has an interior node. So what happens to our Pascal triangle? We only have additional triangles. and that tells us which component we need to exclude to reduce from Lagrangian to serendipity elements. So if we exclude these components that are in this triangle, then we can have a serendipity element. So remember the difference between the two. Terminology is very important in FEA. When you are writing a report or reading a paper, it's important to know what the author is referring to. The other important concept is the Jacobian matrix. Because in FEA we keep moving from local into global coordinates, it's very important to know what would be the equivalent in each scenario. In terms of 1D, we didn't have to worry about it because we didn't have any surface or volume. But when it gets to 2D or 3D, we are dealing with surfaces and volume. So when we are moving from one coordinate to another, actually the surfaces, the value for the surface and the value for the volume is changing when we are converting from one coordinate to another. So here, if you want to find if you want to find the derivative of fxy with respect to kc, you have to use the chain rule. And remember, this is a 2D problem, so we have two components: partial f with respect to x, partial x with respect to kc, and partial f with respect to y, partial y with respect to kc. And if you want to find partial f with respect to eta, the same thing. We use the chain rule, and it needs to have two components because it's a 2D. I can also write that in terms of a matrix form. And I call these partial x, partial kc, partial y over partial kc, and the second row, partial x over partial eta, partial y over partial eta, a Jacobian matrix, which relates the local coordinate to the global coordinate. So this is the global, this is the local. So if you want to find the values in local coordinate, you need to multiply the Jacobian value by the information that we have for the global coordinate. And if you want to do the inverse of that, you just need to inverse your Jacobian matrix. So here, in addition to that equation that we have for Jacobian matrix, it has a physical meaning as well. And the physical meaning of the Jacobian is the volume change between natural and global coordinate. So that's the ratio of the volume that you find if you use your local coordinate to the volume that you find if you use your global coordinate. Let's look at that. That's the relation between our local and global. And you can check that if you put x as 0, for kc we get -1. This is x0 for us. We get kc -1. If you put y0, you get eta -1. So that's the relation that we have for between kc and x. If I take a derivative from each side, d kc would be 2 over L dx, d eta would be 2 over W dy. And if I'm interested in the area, I have d kc d eta dx over dy. So this would be the value that I have to multiply if I'm moving from one area to another area. So that's we said Jacobian is the change between the two volumes. And then here, the volume for us, you just need to multiply by the thickness if you have the area. And that thickness is the same regardless whether we are using a local coordinate or global coordinate. So technically it's cancelled out. So then the difference between the two would be our Jacobian, which would be 4 over LW. And the inverse of that, the inverse of a fraction, if it's a matrix, we have to do matrix inversion. But here, for us, in this simple case, we have a fraction. It's simply L times W over 4. L is one dimension, W is the other dimension, and over 4. If I don't want to use this equation and just look at it and use it based on the physical meaning of Jacobian, I would say that what is the volume if I use xy coordinate? Of course, I have the thickness and then the area. What is the area? L times W. So Vx y is simply TLW. What if I want to use Kc and eta? So this distance based on my local coordinate is 2, and then this distance is also 2. So it's 2 times 2 times t. So you can see if I divide these two, this is 40 and this is TLW. So 4 over LW. That's what we got here. So Jacobian is simply the change of the volume between one coordinate and the other. For a linear quadrilateral elements, usually we have in 2D, we have 2 degrees of freedom per node. So same thing that we did for U, we can do for the other degrees of freedom as well. So this was our displacement in x direction as function of our coordinates. We can do the same thing for the displacement in y direction. We'll find exactly the same shape functions. If we want to write them together in one matrix and call it our displacement field, then our nodal variables matrix would be 8 by 1. We have 4 nodes. Each node has 2 degrees of freedom, one in x and one in y, so that we are going to have 8. And our shape function matrix will be also 2 by 8. So our displacement field would be 2 by 1. So basically I did not calculate new shape functions. I just used the same shape functions for x direction, also for y direction as well. Now we're going to find a strain in linear quadrilateral element. What are the strain values? If we have the displacement field, that's what we found earlier, the strains epsilon xx would be partial u over x, epsilon yy would be partial v over y, and gamma xy would be partial u over y plus partial v or nu over x. So I just need to take a derivative of the first row or the second row, and also because this is 3 by 1 matrix, I need my gamma xy as well. So the first row, everything that I have is just by partial x. So partial n1, partial x, the second component 0, third component partial n, the second shape function over x, and so forth. The second row is the same. For the third row, I have to take partial of the, with respect to y of the first row, partial with respect to x of the second row, and then add them together to get my third row. So this matrix that I find is called B matrix. So that's a very important definition, B matrix. So what is this B matrix? Is the coefficient of my displacement field that gives me my strain. So if I want to find strain, all I need to do is to multiply my displacement field by the B matrix. It gives me strain. So B matrix is the bridge between displacement to a strain, and is used in our calculations. So let's remember this definition of B matrix. So B matrix would be a property of our element. Different elements have a different B matrix, because B matrix is simply a derivative of our shape functions, and we know shape functions are characteristics of elements. Here I'm gonna actually do the math to find the B matrix. So according to the chain rule, if I have my shape function with respect to x, because the shape function is given in terms of my local coordinate, I need to use the chain rule. So n with respect to Kc, Kc with respect to x, same thing with respect to eta, eta with respect to x. I know the relation between the two, so I'm gonna do only for the first shape functions here. N with respect to x would be n1 with respect to Kc. So that would be, if I partial n I with respect to Kc, I have 1, negative 1, 4, 1 minus eta. That would be this part. The second part, partial Kc with respect to x. So if I have d Kc would be 2L dx. So d Kc over dx would be 2 over L. So I have 2 over L here. So my chain rule has another component here. But n1 with respect to eta, I can find this value. But eta with respect to x, there is no x here. So eta with respect to x would be 0. So I don't need to calculate the second component. It would be 0. And if I do the simplification, you would see that that's what I get. That negative would be eta minus 1. I have 2 here. I have 2 over there. And that's the value that I find for the first component. And then I will do the rest for the other component. So this is our B matrix, which is function of our coordinate. Now we want to use that B matrix. We developed the B matrix to find the stiffness matrix. The procedure to find the stiffness matrix is very similar to procedure that we use for beam elements. We use the potential energy and we try to minimize the potential energy based on our displacement field to find the stiffness matrix. This is the potential energy, is the strain energy with the work done on the sample. So if we have the strain energy, I can replace this sigma based on the Hooke's law. We are not dealing with 1D, so I cannot simply write sigma equals E epsilon. I have to use the elasticity tensor, C. So if I replace that, I have epsilon, C epsilon here because we had 2 epsilon. And if you want to have any matrix multiplication, I need to transpose one of them. That's why you can see this one is transposed. So epsilon, I can simplify that. I found epsilon based on U, and I'm using the B matrix. So epsilon, I have 2 epsilon here. One is a column matrix. This is a column matrix. That's the value that I have. And this one is a row matrix. So it's just the transpose of that. And then we talked about that if you want to transpose a multiplication, would be you have to change the order as well. So if I replace the value of epsilon, I find it based on U. And if I put the potential energy, the first component would be the strain energy. The second component would be the work done on the sample. I'm going to minimize that, so set it into equal. And that's the equation that I get. And if I compare it with F equals KU, I can find my stiffness matrix. So the stiffness matrix for a quadrilateral element is the B matrix transpose, elasticity matrix, B matrix, dV. And C matrix is the elasticity tensor that you need to plug in the value, whether you're having a 3D model or 2D model, plane stress, plane strain, that elasticity tensor will be different. So again, here, that's the equation that we ended up driving. B is the strain coefficient matrix, or it's usually referred to as B matrix. C is the elasticity tensor that is different for different 2D assumptions. Whether we're using plane stress, plane strain, or axisymmetric, you're going to have a different elasticity tensor. But we have to deal with that dV as well. That volume is T dx dy, but everything else is based on local coordinates, so I need to convert it to local coordinate as well. And we introduced the concept of Jacobian. If I want to move from x to y and write it based on my local coordinate, I should use inverse of Jacobian matrix. So dV would be TWL over 4. We already found the Jacobian, the inverse of Jacobian, which is WL over 4. If I replace that, this is the equation that I get for my stiffness matrix. So for the case of 2D, for the case of quadrilateral element that we've been talking today, what is the order of B matrix? Do you remember? B matrix was relating epsilon, which is 3 by 1, to our displacement field, which is 8 by 1. So our B matrix was 3 by 8. So B matrix is 3 by 8. Then B transpose would be 8 by 3. And elasticity tensor for a 2D case, whether it's plane stress or plane strain, is 3 by 3. So can you tell me what would be the order of our stiffness matrix? Our stiffness matrices would be 8 by 8. And that's what we expected, because we have 8 degrees of freedom for a linear quadrilateral element. So for a linear quadrilateral element, our stiffness matrix would be 8 by 8. And that's how the stiffness matrix will be formed. And this is the stiffness matrix for only one linear quadrilateral element. Once we have the stiffness matrix, then the procedure is the same. We find a local stiffness matrix for each element, then we put them together to find the global stiffness matrix. We apply the boundary condition, we find a nodal displacement based on that, the stresses, the strains, and so forth. So our task was to find the stiffness matrix that we did. The rest would be the same as any other FEA procedure.